Okay, so today we're going to be doing question number 4 from test number 3. In part A, they want us to predict the reading of the voltmeter and the sign. Okay, so the first step that I do is I find which direction the mobile charges are going in this problem. And we know that in the problem statement it's given to us that the mobile charges are positive. So they'll be coming from the positive end of the battery, and they'll be going through here. So I know that V will be going that way. And to find the sign of the voltmeter, which I'll do first, I have to know what direction those charges will end up being forced. So to do that, I use the formula F of B equals QV cross B, where B is magnetic field and V is the velocity, and Q is the charge. So I know there's plus charge, so this is going to be plus, and by cross product I use the right hand rule, so I do V cross B, and the magnetic field is coming out towards us, so it's this way. So then I know the magnetic force is going downwards, okay? So FB, okay, and because I know the force is going downwards, that means that positive charges will be forced to the bottom of the box, leaving a net negative charge on the top. And because the positive end of the voltmeter is connected to the top of the box, I know that the sign reading on the voltmeter will be negative. Okay, so right here we know that the sign is negative. The next thing we have to do is calculate the value at that spot. Okay, to do that, I'll use the loop rule, which means that the round trip potential has to be 0. So I know that through that, I know that 1.2 volts minus whatever the voltage is inside of there has to equal 0. So to get the voltage going this way, I just use the formula E electric field times distance. Okay, so I'll call this E parallel because it's parallel to the box, times distance, and in this case it's 11 centimeters. So that's 0.11 meters. And if we solve that for E parallel, we get E parallel equals 10.91 volts per meter. Okay, and now that we've got that electric field, which is also in this direction, we can then find the velocity of the mobile charges through the formula V equals mu E. And mu is the electron mobility, which was given to us in the problem to be 3 times 10 to the negative 5 meters per second over volts per meter. And we just calculated E. So if we plug in those numbers, 10.91 times 3 times 10 to the minus 5, we get V equals 0.000327 meters per second. Okay, and we still have to end up finding the voltage, so there's more steps that we've got to do. Okay, so I'll erase what we've got up at the top right here. Okay. The next step is to know that the force downwards, the electric force downwards, the magnetic force downwards, which we saw earlier, which was QV cross B, is going to be equal, after a certain amount of time, is going to be equal to the electric force upwards, because the forces will end up canceling each other out. Okay, so from that we can get the formula FB mag equals FE mag. Okay, and then we use the formula for the magnitude, which is just QVB equals QE. But this electric field is the electric field created by the positive charges that have now migrated to the bottom of the thing, bottom of the box, so that electric field will be pointing upwards, and so therefore I'll call that E perpendicular. And when we can cross out Q because the charges are the same, and we've now solved V, so we can end up finding E perpendicular equals the value of B, which is 1.8 Tesla, times the velocity that we found, which was 0.000327 meters per second. Okay, and we can, that number will be 0.000589 volts per meter. Okay, so that's E perpendicular. And now finally, to find the reading on the voltmeter, we just use that electric field times the distance that it covers. So in this case, it's the height of this box. So it'll just be the voltage equals 0.000589 volts per meter times 0.03 meters, giving us the final solution for the voltage to be equal to 1.8 times 10 to the minus 5 volts. Okay? So this is our final solution for part A. Okay, and now for part B, they ask us to find the sign and reading on the ammeter over here. So the sign is easy because the sign of the ammeter is just what if the sign of the ammeter will read positive if the conventional current enters its positive end, and it will read negative if the conventional current enters its negative end. So we know conventional current is the movement of the positive charges, and we know that the battery's positive end is connected to the positive end of the ammeter. So we know that the sign of the ammeter will be positive. Okay? And now to find the reading of it, I simply use the formula I equals NAV, and I is the electron current. So to get the conventional current, I do big I equals QNAV, and we got V from our first problem, and the area is the area of the box, which is 0. In this case, it's going to be 0.03 meters times 0.02 meters. Okay, so that's A. And Q, we know, equals 1.6 times 10 to the minus 19 coulombs. And V, we know, is that. So simply using this formula, once we plug all of them in together, I equals QNAV, we get the final reading, A equals 2.2 amps. And that's easy and just a simple way to solve part B of this problem.